Hey guys, you guys have any questions about homework? Any questions about homework?
No.
All right. If you would like me to explain anything, feel free to ask me. So, the wrong question, let me pull the answer up. The wrong question was actually number 8. So I think in number 8, the answer was the square root of the actual answer. So if you got that wrong, then you took the square root in the end, which you shouldn't have. So Fiona has a question. You have a question?
Yes. Is that when, like, for example, for number 2, it says how there were three pencils placed like in the shape of a triangle, like each triangle. But like, so then the mass 1 and like one of the masses, the distances. How would we calculate the distance between one of the pencils and 2 other pencils? Because the 2 other pencils aren't placed in the same place.
Well, we don't have to calculate the force like as if 2 pencils were 1 pencil. You can just calculate the forces individually and then use vector addition to add those forces together. So maybe I'll draw out a whiteboard here. So if we have the pencils like in this formation, then we've got one force going this way, one force going this way. So now we just use a vector addition to add these 2 vectors together. All right? So does that answer your question?
Yes, thank you.
Okay. Any other questions? Okay, all right. So I'm gonna wait a few more minutes for people to come in. All right, so if you just entered, if you have any questions about homework, feel free to ask me so I can answer those questions. So maybe I'll wait one more minute. So once again, if you have any questions about homework, please ask me right now so I can explain those. Okay, I'm going to share my screen now. So this week's topic, as you see on the screen, work and energy. All right. So actually, work and energy is very, very critical in all of physics. And you're going to be dealing with work and energy throughout all topics in physics, not only mechanics. You're going to talk about it in heat, and you're going to talk about it in electricity, all that stuff. So work and energy is very critical. So we're going to be spending around 2 weeks on work and energy. So this is the first week, more like an intro to how work and energy work. All right, so I'm going to get started now. So the topics we're going to discuss today are work, and then kinetic energy and potential energy. So if you've taken any middle school science class, some of these words might be very familiar to you. And we're going to go over in depth about those later in the class. All right. So work. What is work? Well, we do work in our daily lives, right? I do my homework. We do work in school. We do work in the office. But in physics, that's not the kind of work we're dealing with. The actual definition of work in physics, so the definition of work is the energy you need to create change. Work is the amount of energy you need to create change in the universe. So what do I mean by creating change? Well, if we have a table and we have a box at point A, if we were to somehow move the box to point B, then we have done work on the object. The box's placement has changed, right? And overall in the entire universe, something has changed, and work must be done to create this kind of change. And another way you could visualize this is if you were to drop a ball and the ball starts moving. If something starts out not moving and then later it has some kind of velocity, then some kind of work must have acted on it, because you need, since something has changed in the universe, the ball's speed has changed. In this case, gravity does the work required to create that change. So work is energy. When you create change, you need some sort of energy. If you were to push a box along a table, you would have to use the chemical energy stored in your food to create that change. And in gravity, that also works in the same way. So the actual physics definition of work, we're going to label this as a W, is equal to the force times the distance. So what do I mean here? Well, back to our example of a box. If we were to apply a force to push this box, to push it to another point, which is a distance d away, we have done work on the box because the box has moved. And this force must overcome the frictional force. We have caused change, okay? So the work, based on the physics definition of work, force times distance, this work equals the amount of force I'm applying times the distance in which this force is being applied. And this makes sense because if the force needed is greater, then you need to put in more energy to push the box. And if you were to push it a greater distance, you would also need more work. You would also need more energy. Okay? So this is the definition of work. Work equals the force applied times the distance in which this force is being applied. And this definition is not actually perfect, because if you were to push a box at an angle, but the box still moves in a horizontal direction, then technically the y component of force hasn't done any work on the box, because in terms of the y direction, the box is not moving up or down, right? So in terms of the y direction, no work is being done. So in this case, we only care about the forces that are acting in parallel with the box's movement. So we only consider the forces that are contributing to how the box moves. So in this case, we only consider the x component of force. So actually, in this case, work equals the x component of force times distance. Okay, we don't take all forces in general. We only take the forces that are going in parallel with the box's movement, right? And if this angle is theta, another definition of work could be the force times cosine theta times distance. All right, so this is the general formula for what work is. So if the force is being applied at an angle theta to the box's movement, then the work would be F times cosine theta times distance, times the distance applied. Okay, because only the forces parallel to the box's movement are actually doing the work. Because other forces, they don't matter. Because if they weren't there, then nothing would have changed anyways. Okay. So what are the units we use for work? Since work is a form of energy, in physics, the unit for energy, any kind of energy, is the joule. All right, it's spelled like this. And Joule was a famous scientist who talked about heat and energy and all that. So we use the unit joules, J. Okay? And in other terms, since work is in terms of joules, force is in newtons, and distance is in meters, a joule is equal to 1 newton times 1 meter. Okay? So those are the units we use for work. So are there any questions about how this works? So the key things you need to take away are the definition of work is the force being applied times the angle cosine theta times the distance. And then the units we use for work is units we use is our joules. Someone's asked me about the M here. The M here is actually meters because this is what we call unit analysis in physics. Because we take the unit of one value, we take the unit of the other value, and we take the unit of a final value. And when these units combine to each other, they create some sort of equation. Okay, so do these problems here. I'll give you guys 5 minutes for these problems. These should be pretty straightforward. So once you get your answer, please chat that to me. And if you would like to present your solution to the whole class, then let me know as well. All right, how about one more minute? Okay, so for number 1, we're going to have Tyler to explain the problem. Okay, so I enabled participants annotation, so I think you'll be able to do that. So take the stage.
So question 1 is pretty easy. You just have this box that's on a surface and you're pulling it with a force. But the box is also resisting with the frictional force, and friction is equal to mu times mg, which is the 0.3 times 50 times 9.8. So that's the force that you have to pull to make the box move horizontally at a constant speed. And you multiply that by 10 meters, and that's your work.
Yep, good job. So for number 2, I'm going to explain this one. So you lift a 3-kilogram box upwards to a height of 10 meters. How much work did you do? Well, if you're pulling upwards, you're going to apply some kind of force, and then gravity will counteract this. So your force will have to equal to mg, and using the work equation, work equals force times distance. So work equals mg times d. So what is that? 3 times 9.8 times 10. So this is going to equal to 294 joules. Okay. So now for the last question, Fiona will explain the answer.
Okay, so for this one, you just use the formula that work is equal to force times distance. So 58 is equal to, and we don't know the force, times 0.5. And if you multiply both sides by 2, this is F is equal to 116, and it's in newtons.
All right, nice job. So are there any questions about how you would do these 3 problems? Okay, cool. So we have 2 more problems here. Once again, maybe I'll give you 5 minutes on these. And once you get your answer, please chat your answer to me. And if you want to explain anything, please chat that to me as well. So for the first one, when it says box is sliding, that means the box will always stay on the floor. It's not going to go up or down. All right, so maybe about 2 more minutes for these problems. Okay, so these are slightly more challenging than the ones on the other slide. Okay, so for the first problem, we're going to have Tyler explain the answer. So go ahead.
This one, you just input the values again. So you have an incline at 37 degrees, and you have this box that you're pulling upwards. So you have a force of 50 newtons pulling, and work is equal to force cosine theta times distance. So you just have 50 times cosine 37 times, I think it's 10.
Yep.
And that's the answer.
And in the end, you would get 399.3 joules. Okay? Now for the second problem, the answer is 0. So first of all, let me present to you an incorrect solution. So once you look at this problem, first when you look at this problem, you might think, hey, well, work is given by force times displacement. And for the force, that's going to be the gravitational force, m times m of satellite, m of Earth, over r squared, times, please stop writing. So let me disable it first. So times the distance, which you would say, oh, that's 1 revolution, 2 pi r, and then you would calculate that. But that's actually not right. So why isn't this right? Well, let's first look at one instant where the satellite is going to be moving. Let's say it's moving this way, velocity, okay? And in which direction is the force being applied? Force is going to be perpendicular to velocity because that's the definition of circular motion. And at any point on this satellite's path, the force is always going to be perpendicular to the velocity. And then if we plug this into our work equation, work is equal to F cosine theta times d. Well, technically our distance is going to be in this direction because that's where the velocity is going. So what is this going to be? F times, what's cosine of 90? Because this is the right angle. Cosine of 90 is 0. So in the end, 0 work is being done on the satellite by the Earth. Okay? So does everyone get how that works? All right. So now we have kinetic energy. So if you've done something about kinetic energy in your 6th grade science class, then you know that kinetic energy is moving energy. Kinetic means moving, okay? So kinetic energy basically is the energy that any moving object has. if an object is moving, then it has some kind of energy. So how do we know a moving object has energy? Well, if this box is moving this way, and it's about to hit to another box that's stationary, when when this box hits the other box, then the other box starts moving, right? And so this energy is being released. This energy will do work, because work and kinetic energy are both forms of energy. And so this box can create change by allowing the other box to start moving. So any moving object has kinetic energy. Okay? And the actual formula for kinetic energy, if we have some mass m moving at a velocity v, then this object has kinetic energy 1/2 mv squared. All right? This is the equation for kinetic energy. So please write this down. This is a very important equation, and you're going to be seeing this quite a lot in the future. Okay? So I'll give you a moment to write this down. So this is the definition of kinetic energy. So if we were to have, I don't know, a 50-gram ball, 50 grams going at 20 meters a second, this would just be 1/2 times 0.05 times 20 squared. This would be the kinetic energy of the ball. If we were to calculate this, we would get 10 joules. Okay? So once again, kinetic energy is a form of energy, so we're going to use the joule to represent it. Okay, so what is the link between kinetic energy and work? Right, because they're both forms of energy. How can I connect these two concepts? Well, let's first start out with work. Work is equal to force, let me write that better, force times distance, right? Or, since F equals MA, MAD, mad. Work is mad, okay? So let's use a kinematic equation to represent work, to represent the acceleration. Remember this guy? V squared equals V0 squared plus 2AD. So now if we were to calculate for A, this would be V squared minus V0 squared over 2D. This would be A. Okay? Now let's plug this guy into this equation. This would be M times V squared minus V0 squared over 2D times D. And as you can see, the D will cancel. And all we're left is M times V squared over 2 minus M times V0 squared over 2. Or in other words, 1/2 mv squared minus 1/2 mv0 squared. And these two, as you may remember, these are the equations for kinetic energy. And work is equal to these. So what does this mean? Well, at the initial, work equals the final kinetic energy minus the initial kinetic energy. Okay? We can represent this as work equals KE final minus KE initial. All right? So this is how we can link work and kinetic energy together. All right, so write this equation down. In other words, work is going to equal to the change in kinetic energy, and we're going to use the delta symbol here, change in kinetic energy. Okay? So these two equations are going to link work with kinetic energy. Okay? And these two are actually the same thing, just written in different ways. So I'll give you a moment to write these down. And along with the definition of kinetic energy as 1/2 mv squared. All right, maybe 10 more seconds to write these down. Okay, so let's do some problems with these. So I'll give you guys, these are pretty direct, so I'll give you 3 minutes, 1 minute for each problem. And once you get your answer, please chat that to me, and I'll let you know if you're right or not. So if you would like to explain one of the problems, please tell me. So I'll let you do that. So Fiona is going to do the first one, okay? All right, so for the first problem, we're gonna have Fiona explain that answer. Okay, so go ahead.
Okay, so for this, we just use the formula because the kinetic energy is equal to 1/2 times the mass, which is 10, times the velocity squared, which is 50, and squared is 2500. And when you do that, that is, wait a minute, 0.5 times 10 times 2500, and that is equal to 12,500 joules.
Yep, that's correct. So 50 meters a second is actually quite a fast speed. So I might have made a mistake when I wrote that problem. So now for the second one, a mass has kinetic energy 500 joules if it moves at 25 meters a second. What is its mass? Well, we can use this equation again. Ke equals 1/2 mv squared. So Ke is 500. 1/2 times mass times 25 squared. So mass will be 1.6 kilograms. Now for the last one, a 50-gram ball has kinetic energy 730 joules when launched horizontally from a baseball player's hand. If the baseball player is 1.5 meters tall, how far did the ball travel? Well, let's first use the kinetic energy equation to see how fast the ball is going when it's launched. 730 equals 1/2 times 0.05 times v squared. So what is this going to be? 730 times 2 over 0.05. Take the square root of that. It's going to be 171 meters a second. That is too fast. I don't think my questions are that realistic. Okay, so now this baseball player is 1.5 meters tall. So now we use the kinematic equations to determine how long the ball is going to be in the air. Well, it's going to start out at rest. So we're going to use this equation here. D equals V0t plus 1/2 AT squared. Let's establish a positive and a negative. So the distance will be how tall the baseball player is, 1.5. V0 is 0, because in terms of y direction, it's not moving. And this is going to equal to 1/2 times g times t squared. So what is that going to be? 1.5 times 2 over 9.8. Square root of that. T equals 0.55 seconds. So now if we multiply velocity times time, we're going to get how far this ball will travel. 171 times 0.55, that's 94 meters. So once again, these problems are a little non-realistic, so don't worry about that. All right, any questions? All right. Now we have these two problems here. These are a little more challenging, so I'll give you guys maybe another 3 minutes for these. Well, how about 4 until 8:40 for me? So once you get your answer, please chat that to me, and I'll let you know if you're right. For the second problem, we're going to assume that the car is going to skid. The brakes will be on, and then it's going to start skidding. Okay, it's going to slide. Okay, how about one more minute? Okay, so I'm going to go through these problems. For the first one, my arm accelerates a ball of mass 50 grams from rest to 20 meters a second within the distance of 80 centimeters. What is the average force I exerted on the ball? So one way we could do this is actually using the kinematics equations, but it's actually a lot easier if we were to use energy, okay? So how will we use energy here? Well, obviously we're going to exert force through a distance that's going to make the ball obtain kinetic energy. And what is giving the ball energy? The work. And if we use the work equation again, work equals change in kinetic energy. So how much did my kinetic energy change? It changed from 0 to the final amount. So it's going to be 1/2 m times v final squared. So that's the change in kinetic energy. This is equal to the work, which is the force I apply, times the distance. So the force will be 1/2 mv squared over d. So what's that going to be? 0.5. I think that's going to be 12.5 newtons. Okay, I didn't do my calculations wrong. So now for the second one, a car is moving at 98 kilometers per hour on the road. The coefficient of friction is 0.4. How far would a car travel until it stops? So once again, we could use the kinematic equations for this one, but energy makes things a lot easier once again. So we're going to use the equation again, work equals change in kinetic energy. Or in other words, you could use work equals the kinetic energy of the final situation minus the kinetic energy of the initial. So initially, the car is going to be moving, right? And finally, in the end, it's going to be stopped. So our final kinetic energy is 0, and our initial kinetic energy is 1/2 mv squared. Now, what's the work being done? Some kind of work must be done for the car to stop moving, right? Because work must be done to cause change. If there's any change in the universe, some kind of work must have been done. So what is the work here? Work is determined by friction in this case. Friction does negative work because it's countering the object's motion. So in this case, friction is going to be negative mg mu. So that's going to be the force of friction. And then that's going to be applied to the distance. So now, what do we have here? We have mg mu d equals 1/2 mv squared. So I've removed the negatives there. Now we can remove the m. And so my distance is 1/2 v squared over g mu. So let me just calculate that quickly. So first we have to turn 98 kilometers per hour into meters per second. And that's going to be 27.2 meters a second times 0.5 over 9.8 and 0 over 0.4. So it's going to skid 94.5 meters. Okay, any questions? So for any of these problems, we could have used dynamics and kinematics because we would have been able to find the acceleration of the car and then use some kind of kinematics equation. But as you can see here, work and energy makes things a lot simpler. But you're going to get the same answer at the end. Okay. Now, finally, we have potential energy. So once again, if you've learned about energy in your 6th grade science class, potential energy is stored energy. So what do I mean by stored energy? Potential energy is the energy stored in an object, and if this energy is released, then it's going to be released to other means. So it might be kinetic energy, it might be heat. Okay, so a common example, probably the only example they teach in middle school, is going to be gravitational potential energy, the potential energy due to gravity. So this basically means that any object high up has more potential energy, because if this object were to fall to a lower height, then that energy would be released. It would be released as kinetic energy because the ball would then be moving. Okay, so potential energy, gravitational potential energy, is caused by how high an object is. Okay, and gravitational potential energy is all relative because we have to compare the initial point of a ball, h, and we have to compare that to the lowest point the ball will go. In this case, it might be the floor. Okay, because at that point, the ball will stop moving. Okay, so potential energy is all relative. If the table were closer to the ball, then h would be a lot smaller. If it were to drop all the way to the floor, then h would be greater. And the equation we use for gravitational potential energy, we'll label that as PEG, that equals mgh, mass times the gravitational acceleration times the height of the object, the relative height, okay? So how do we derive this? Well, just like in the example I gave you a little earlier, if we were to push a ball up and do work on a ball, then that would equal to mg times h, right? We would do work on this ball. And where did that energy go? That energy would be stored inside the potential energy, okay? So that would be how we would derive the equation for potential energy. So please write this down, quite important. The potential energy due to gravity is going to be mass times g times h. All right, so now we have other types of potential energy as well. We can have electrical potential energy, stored energy in batteries and stuff like that. And a common one we use is called elastic potential energy. Okay? So what is elastic potential energy? Elastic potential energy is the energy stored in springs or stretchy objects. Because if you were to have a spring, right? And if you were to compress this spring, then if you were to release the spring suddenly, then the spring will shoot out. It's going to shoot out and release the stored energy inside it as kinetic energy, okay? So springs and rubber bands and all that stuff have elastic potential energy because if you compress them or stretch them, they're going to snap back and start to move, and they're going to release that energy as kinetic energy. So in springs, if we were to compress this, as we know, if we were to compress a spring, it would try to push itself back out, right? The springs want to be in their relaxed position. They don't want to be stretched. They don't want to be compressed. And this position is what we call the equilibrium position. Equilibrium is where the object is where the string is not compressed or stretched. But if you were to compress it, it would try to exert a force to get back to that position. So what is this force? This force is given by K times X. So let me break down this formula here. So what is K? K is what we define as the spring constant, or the stiffness of the string. So what do I mean by stiffness? Well, if you were to take the spring inside a mechanical pen, then it would be very easy to compress because it's very thin, it's very light. But if you were to take the springs inside a car, they're really stiff, and they're really hard to compress. So this is what we call the spring constant, okay? And then we have X. What is X? X is the displacement of the spring, how much distance we have compressed it from the equilibrium point, okay? So the farther you would compress it, the more force there would be. So this is the force due to a spring. So we're not going to actually use this that much right now, but this formula is going to come really in handy later on when we talk about more in depth about springs. Okay, so first keep this in mind. So what is the elastic potential energy stored in the spring? Well, the elastic potential energy is going to be given by 1/2 kx squared. Okay, this is the elastic potential energy. So once again, if the spring is stiffer, it's going to have more potential energy. And if you compress it more or stretch it more, it's going to have the same potential energy. It's going to have more potential energy as well. Okay? So both of these equations apply to both compressions and stretches. Okay? So it doesn't matter if it's being compressed or stretched. Both of these equations will be applied. All right? Any questions about springs? And yes, X is the displacement of the spring from its equilibrium point. At its equilibrium point, once again, the spring is unstretched and it's going to be relaxed, okay? That's the point in which the spring would be if there was no force acting on it, if it would just be relaxed like that. And X would be how much shorter or longer it would be, all right? So these are the two equations you should remember. All right, so we have these two problems here. So I'll give you guys maybe 2 minutes for these. So these are about gravitational potential energy, these two. Once again, when you get your answer, chat that to me and I'll let you know if you're right. So 1 more minute. Okay, I'm going to explain these now. So for the first one, take the potential energy at the top of a 2-meter tall table as 0 joules. So remember, potential energy is all relative. So if we take the top of the table as 0 joules, then we will compare all values of potential energy to that point. Okay? So if we lift a 7-kilogram box to a height of 10 meters above the table, then relative to the point we've comparing it to, this would have a height of 10. So then we would just use the equation PE equals mgh. So what is this going to be? 7 times 9.8 times the height, which is 10. So what would this be? This would be 686 joules. So now for the other part, if the box drops to the floor, it would be -2 in terms of in terms of negative. I'm talking about the box is under the table now. So it's going to be a distance of -2. So then if we just plug this in again, PE equals 7 times 9.8 times -2. This would be -137.2 joules. All right, so once again, potential energy is all relative. So potential energy can in fact be negative. Okay, so that's something you should remember. Now for the second one, a 3-kilogram box falls from a building of height of 10 meters. Assuming that 80% of the box's potential energy was converted into kinetic energy, what is the box's speed just before it hits the ground? So 80% is 0.8. So 0.8 times the potential energy equals the final kinetic energy. So let's plug values in here. 0.8, remember potential energy is mgh. 3 times 9.8 times 10. Kinetic energy is 1/2 mv squared. So now we just need to solve this for v. So 0.8 times 9.8 times 10 times 2. And take the square root. It's going to be 12.5 meters a second. Okay? So now where did the lost energy go? Well, the lost energy can be due to air friction, air resistance. And when the air molecules rub against the box, it could create heat. And heat is also a form of energy. So there are a lot of ways in which this energy could go. So are there any questions about how you would do these problems? All right, cool. So now I've got two problems about springs. And once you get your answer, please chat that to me. So I'll give you guys 3 minutes for these problems. So here's an extra challenge for you for the first problem, and another part for it. All right, so we're running a little low on time here. So I'm just going to explain these now. If you haven't finished yet, feel free to keep going. So now for the first problem, you compress a spring 3 centimeters, which requires 394 newtons of force. What is the spring constant of the spring? Well, let's use the equation. Force is equal to the spring constant times the displacement. So what is this going to be? 394 equals K times 0.03, right? Because we have to turn centimeters into meters. So our answer is going to be K equals 13133. So now what is the unit of K? This is a unit analysis practice here. So once again, how would you solve for the units of K? Well, force is in newtons. Newtons equals, well, whatever unit's going to be here, times x. X is in meters. So how do we turn meters into newtons? Well, if we multiply this by newtons and we divide this by meters, then we'll get there. So the units for K is going to be newtons over meters. So that's how you would find it by unit analysis. So now we have a vertical spring of constant 130 newtons per meter hanging from the ceiling. Oh, I added that there on accident. And then you quickly hang a 25 kilogram mass on it. The spring bobs up and down until eventually it stops moving. How much longer is the spring now? Well, if it's bobbing, well, by common sense, if we immediately put a mass on it, it's going to bob up and down until eventually it stops moving. So we don't actually need to care about the fact that it's bobbing up and down. All we need to care about is the final location of the spring. When it's hanging like this, the mass has gravitational force on the spring, mg. And this is the force that we're going to use in our calculations for how much longer. That's going to be x here. So mg, which is F, equals K, 130 times x. So what's the answer going to be? 25 times 9.8 over 130. X is going to be 1.88 meters. So that's how much longer it's going to go. So now how much energy is stored in the spring? Well, now we have x, so we can just do 1/2 kx squared as the energy. So remember this. So it's going to be 1/2 times 130 times 1.88 squared. So if we do that, we're going to get 231 joules of energy. Okay? So are there any questions about this? Alrighty. So that's going to be it for today. So I hope you guys enjoyed, and I'll see you guys next time. Bye.
Thank you. Bye.